Hey class, it's Mr. M, here to introduce you to the sometimes complicated idea of related rates. The basic concept here in terms of the actual arithmetic and the procedure, and we'll get into some of the more conceptual stuff in class, but the procedure is basically going to involve implicit differentiation. And how this is different from what we've seen in implicit differentiation in the past is rather than using the derivative with respect to x, or the change with respect to x, we're going to be using the change with respect to time, or dt. And typically, t is not going to be one of the variables in our equation. Recall that when you take an implicit differentiation problem, for example this one here, to find the derivative with respect to x, you treat all the problems, all the terms exactly as you normally would with any derivative rule. And here we're taking the derivative with respect to x, but anytime you have a mismatch in your variable of differentiation, which is this x down here, and the variable you're actually taking the derivative of, which is this y, for example here, then you have to chain on dy dx, in this particular case, y coming from the problem, and ddx coming from the derivative you're taking. The chain rule has to append onto the end in order for you to take the derivative. So an application here would be 3y squared, and since you have a mismatch, dy over the dx that we took, plus 2y, again there's a mismatch, so dy dx, equals, on this side we don't have a mismatch, so 3, and then the derivative of 5 is 0. And then from here it's very familiar arithmetic, dy dx, factored out, 3y squared plus 2y, divide, and you have your answer. So it's that first step really that's important. From then on it's typical arithmetic. It's right here. Anytime your variable of differentiation, which in these problems used to be x, your variable of differentiation is going to be a t in these examples. So let's do an example here with without any actual application, just purely the procedure. That way the actual application will make more sense in just a minute. So this question is asking us to find dy dt for this particular equation here. Well, even if that's a little unfamiliar to you, which it may be, let's focus on the fact that this is the difference from previous problems. It's not dy dx, it's dy dt. So, implicit differentiation, take the derivative of both sides, but since our answer needs to be dy dt, let's take the derivative with respect to time. And maintaining equality, do it for both sides. So the derivative of the first term, well, here's a mismatch, isn't there? It's x, but we're taking the derivative with respect to time. So take the derivative as you normally would. Here this would be 6x, but since there's a mismatch, x and t, we're going to chain on dx dt. Okay? And here we have 10y. Again, we're taking the derivative with respect to time, so chain rule dy dt equals 12, the derivative of 12 is 0, there's a mismatch, times, you could think of this as d12 dt I suppose if you wanted to, but 0 times anything is 0, so that's convenient. So now we have 6x dx dt is equal, plus 10y dy dt is equal to 0. And we're looking for this thing here, so subtract the other term over. 10y dy dt is equal to negative 6x dx dt. Divide in order to get dy dt by itself, so dy dt is equal to negative 6x dx dt divided by all of this, which is 10y. Not a very pretty answer, but there it is. Dy dt, y changes as a function of time. The change in y over the change in time is that ugly equation over there. So here let me give you an example of why we actually study something like this. Why do we take the derivative or investigate the change of things with relation to time rather than relation to each other? And in a sense you already understand intuitively how this concept might work. If you've ever filled up a cone of water or a cone cup of something like this type that you have here, in this beautiful drawing I'm filling in, you know that with the water coming in at a constant rate, the cup is going to fill up really fast and then kind of slow down. So it starts off filling very quickly and the water level rises, but then it starts to rise more slowly. And that is illustrated best through related rates. It shows that as time progresses, the rate at which the height of the water changes depends on the rate of volume, or the volume of water coming in. So there are some relations that are going on here that intuitively you may understand, but mathematically require a little more nuance. So let's take a look at an actual example and dive right in. Here we have a classic related rates problem. A 10-foot ladder leans against a wall. It's on slick pavement and slides away from the wall at a rate of 4 feet per second. How fast is the top of the ladder sliding down the wall when the base of the ladder is 8 feet from the wall? Now, I know what you're thinking. How on earth could this possibly happen in real life? This sounds so contrived, and honestly, in some senses it is. But it's a very simple example mathematically that allows you to see how these rates relate together. Some of the more real-world examples make a lot more sense in terms of reality, but the actual math can be more complicated. But this silly problem will help us at least see the math. So try to picture what this looks like. Maybe even sketch it out on your notes, and then, as you pause the video, sketch it out, and then see if your picture looks something like mine. Alright, perhaps you paused it, and now you're looking at this beautiful work of art. Wow, quite a picture. Well, we have our ladder. It's sliding away. It's 10 feet long, and as it slides away, as you can imagine, the top of the ladder here will slide down the wall as the base of the ladder is sliding away because of the slick pavement. We know a couple of parameters here. We know that the base of the ladder is sliding away at a rate of 4 feet per second. Okay? We also know that this value down here, the length of how far it is from the base of the ladder to the wall, is changing, because as the ladder falls down, as the ladder slides away, it's getting farther and farther away, and likewise the height of the ladder up against the wall is getting smaller and smaller and smaller, right, as time goes on. As the ladder is pulled back away, the top of the ladder comes careening downwards against the wall. So those values are going to change, so we have to ascribe to them variables, not numbers. So since this is a horizontal distance, I'm going to call this x. And since this is a vertical distance, I'm going to call this y. The actual question we're asked, if you look back at the text, is how fast is the top of the ladder sliding down the wall? So that's here. How fast is it sliding down the wall when the base of the ladder is at exactly 8 feet away? So translating this complicated, strange phrase into math is quite a difficult skill. So the top of the ladder is modeled by this variable here, y. If y is a certain value, then that's where the top of the ladder is. If y is 5, the top of the ladder is 5 feet up the wall. If the y is 10, then it's 10 feet up the wall, or what have you, right? So we want the speed, or the rate. How fast is the top of the ladder sliding down the wall? So we know that y is going to be involved here, because that tells us how tall or how high up the wall the ladder is. And the question is how fast, and that's a rate. And speed, rate, derivative is the key idea you want to take away from that. How fast tells you that you want the derivative. So the change in y, and since we're talking about speed, we want it dy, the change in y over the change in time. Right? The y value can change by 10 feet, but 10 feet in half a second and 10 feet over 30 seconds are very different speeds. One's very fast, one's very slow. So we want the speed. What we're looking for is dy dt. How fast is the top of the ladder sliding down the wall? Dy dt. That's what we're looking for. And we have a condition that is going to occur when the base of the ladder, right, when the base of the ladder is 8 feet from the wall. Well, what models that? Well, the base of the ladder is here, and the number that will tell you how far it is away from the wall, we've already called x. So we want dy dt when x is equal to 8. That's when we want this problem to occur. So, that's not necessarily very easy. How can we approach this? We have x, we have y, and we know the ladder remains 10 feet in length. Here's x, here's y, and here's 10. So we need to think of an equation or a formula or some idea, and I'll be honest, these ideas normally come from geometry, that relates these values together. And this one should be obvious. How do x and y and 10 fit together in the configuration that we have here? Well, that's of course the world-famous Pythagorean Theorem. Alright, well that's a start. X squared plus y squared equals 10 squared, or of course x squared plus y squared equals 100, to make it easier on ourselves. Well, what do we want? We want dy dt. And an equation like this should look a little familiar by now, right? It's an equation that is implicitly defined. X and y are implicit functions of each other, and we just took an implicit derivative a couple slides ago. So let me go back there temporarily. Right here. Here's an equation that was a lot like this. We had something x squared and something y squared equals a number, and we found the derivative not with respect to x, not with respect to y, but with respect to time or some other variable t. And in that scenario, any time you had to take the derivative of something that was not a t, you had to chain on d, that variable, dt. For example, dx dt or dy dt, right? So the same thing will happen here. And it should be clear that we should do that because, again, our goal that we defined a minute ago was dy dt. That's what we want. So hidden within this equation is dy dt. We just need to extract it. Okay? So, let's see what this looks like. Let's take the derivative, and I'll do this on a new slide. X squared plus y squared equals 100. We want dy dt, so let's take the derivative with respect to time. This will give us a rate. So the first part is 2x, but there's a mismatch, so dx dt plus 2y dy dt, the derivative of a constant number with respect to anything. The change is 0, there's nothing changing. It's always 100. The ladder is not getting longer or shorter. Right? So now we have this complicated function with a lot of moving parts. Let me underline here all the things that are not numbers. We have x, we have dx dt, we have y, and we have dy dt. Now, one of those we already know we're looking for, right? That's our goal. We're not going to be given that value. So it's okay if we don't know what that is. The other ones, though, we should be able to figure out. So let me pause the video for myself here and put a quick sketch of what we had on the last slide. That way we don't have to go back and forth. Alright, so this drawing has just popped up for you, and again, here's the scenario that we have. X and y, 10-foot ladder, is being pulled away at a rate of 4 feet per second. We're looking for dy dt, which we have in our equation now, and we know that x is equal to 8. So we know what x is equal to, right? That's not an unknown. But we still have several unknowns here. For example, what is dx dt? That's peculiar. No one gave us dx dt. We're not looking for it either. So for this problem to be solvable, we need dx dt. Well, what is x? X, if you look back at our model here, is how far, remember this is the building, here's the ladder, it's 10 feet long, and then x is how far the base of the ladder is from the wall. Well, don't forget, the only reason that this is a calculus problem and not just a simple geometry problem is the ladder is sliding away because of the slick pavement. Right? It's falling down. So the base of the ladder is moving farther and farther away as time goes on from the base of the wall. Right? So at this moment, it might be 10 feet away, but a little bit later, it'll be 12 feet away, and so on. Right? It's getting farther and farther away because of the fact it's being pulled away, it's sliding back. So dx dt is the rate at which it is moving back, which, if you recall, we currently know. If you go back to the original problem, it says the ladder is sliding away from the base of the wall at a rate of 4 feet per second. So dx dt is 4 feet per per second. That's how much x is changing, right? That's the horizontal distance, the slide, as a function of time. But we do not know y, right? That's still missing. So, how do we find y? Well, we've got to put our geometry hats back on and look back at our scenario. We have x squared plus y squared equals 10 squared. And don't forget, we were given that x is equal to 8, so really this is 64. 8 squared plus y squared equals 10 squared, 100. Subtract, and y squared is equal to 36. So y is equal to 6. Technically plus or minus 6, but this is a real-world scenario. We have a positive height here. So the problem told us that x was equal to 8, but what they implicitly told us is that y was also equal to 6 because of the Pythagorean Theorem. So really, we do know what y is. Y is equal to 6. And if you look at your equation now, you have known values for everything, right? We already established that x was equal to 8 here. Put a check mark. So we know x, we know dx dt. We had to figure out what that was in the first place. And we used a little bit of geometry to figure out what y was. So we have all of our known values. We can now find our derivative. So plug everything in. You have 2 times 8 times 4. Right? This 2 came from our equation. The 8 and the 4 we just plugged in. Plus 2 times y, which is through geometry we found to be 6, times dy dt is equal to 0, because the slope of 100 is 0. So this will give you 2 times 4 is 8, times 8 is 64, plus 2 times 6 is 12, dy dt equals 0. Subtract 64, 12 dy dt is equal to negative 64, divide by 12, dy dt is equal to negative 64 over 12, which reduces to negative 16 thirds, which is approximately negative 5.333. Well, what does this number mean? We found dy dt, but it's a negative number. It's not particularly pretty. We also don't know what unit it's in. We've got to fix that too, because we have to understand what our answer actually means and not just have a ridiculous number here. Okay, so let's ponder all those questions here together. I'll leave some space here for the unit. First of all, a value is negative. How does that make sense? How can you have a negative rate? Well, it should make sense. Our ladder is moving down the wall, right? It's moving far away, and as this is happening, the ladder is moving down the wall. So the fact that it's negative should make sense. As time moves on, the height of the ladder is decreasing, right? It's eventually going to hit the ground and hit 0, but until then it is decreasing. So the fact that it's negative should make some sense. The next question becomes the unit. And here's a great trick. And it's not really a trick, it's really a mathematical understanding of this problem, but it's a good way for you to understand how these units can come into play. What we have just found is dy dt, right? The change in y over the change in t. And earlier in class, several weeks ago, I've mentioned to you when we first talked about implicit differentiation, is to keep an eye out for units, right? When you think about the derivative as a rate of change, your rate of change is a slope, and your slope is the change in the change in y over the change in x, typically on a typical coordinate plane. Well, here we have the change in y, and here we have the change in t. These are arrows. And y is a measurement in this scenario of how high this thing is off the ground, right? The top of the ladder against the wall. And that's a measurement that is made in feet. You don't measure height in seconds or hours or grams. You measure height in this problem in feet. And likewise, dt is the change, the difference in time. And you don't measure time in feet or inches or anything else. You measure time in this problem in seconds. So the derivative that you find, right, the d whatever dt, is always going to tell you what the unit is. So dy dt, y is measured in feet, that's on top, dt is on bottom, t is measured in seconds, so negative 5.33 feet per second. And if you go all the way back to the original problem, the question was, how fast is the top of the ladder sliding down the wall? feet per second is an answer to the question, how fast? How fast was it going? Negative 5.333 feet per second. And there you go. There's a very basic, typical, standard, classic related rates problem. Okay, so this video is running a little long. I understand that. I want to show you an itemized list or a procedure of what we just did in this problem. And don't worry about writing it all down, because I'm going to give you this procedure in class, and it's going to be printed out, and you don't have to follow it religiously by any means, but it can kind of give you a structure to the way you approach a problem like this. And if you prefer your own structure, by all means, follow your heart. So here it is. The first thing we did in this problem was to draw a picture. It always helps to understand the scenario here. And we didn't quite do this second, but we did this pretty early on. We identified what we needed to find. And in this particular problem, the question that was asked, right, the actual question mark in the written question was, how fast is the top of the ladder sliding down the wall? So we realized that in our picture we call that y, and since it was a rate, it was how fast, the derivative of y with respect to time. That's what we needed to find. We then labeled the given numbers in terms of variables and derivatives. So we knew that the x was how far it was off of the from the base of the wall, and y was how high up the ladder was off the top of the wall. And a little bit later, we realized that the 4 that they gave us was dx dt, right? That was going to equal 4. That's how far it was being. That's how fast it was being pulled away at that rate. Okay, so we labeled our variables, the numbers they gave us, right? X was equal to 8, for example, at our specific instant. The next step was to use geometry to connect the variables. So we have x, we have y, we have this 10, which is the length of our ladder. That was also given to us. Well, what connects them? Well, that was the Pythagorean Theorem. So that's the key insight, is to recognize that the Pythagorean Theorem in this problem and other formulas and other geometry problems will allow you to relate x and y, or whatever your variables happen to be, to each other, right? We then, once we had an equation, we simply took the derivative with respect to time of both sides, and that gave us 2x dx dt plus 2y dy dt equals 0, right? Once you have your equation from geometry, simply take its derivative with respect to time. Next, we plugged in the known values, right? So those were the x, that was 8 that we were given, dx dt, right? We knew that that was 4. Let me write some of these down so you can visualize these. Dx dt, we were given that was 4, but we didn't have y. We needed y, if you recall, but we didn't have it. So we had to go back and figure out what y was, and we found y by using the Pythagorean Theorem, and y had to be 6. Right? So we had to do some problem solving there to fill in what we needed in order to have dy dt to be our only unknown, which is fine because we're looking for it. Now this part here that I'm mentioning, if needed, use geometry to eliminate a variable before differentiation. That is for more complicated related rates problems, for example, dealing with cones or pyramids or other shapes that use similarity, as we'll see. So we didn't actually use that step really in this one, except for the fact that we found y by using the Pythagorean Theorem. So plug in known values and rates after you've taken the derivative. Now that's a very important step that I haven't made quite as clear as I need to, as we're just starting out. You only plug in numbers after you take the derivative, which should make sense, because if you plug in the numbers first and you take the derivative of a number is always going to be 0, right? If it's of a constant static number. So take the derivative and then plug in your values in order to actually have the change occur without having a static situation. Finally, once you've plugged in those values, the only variable left should be the one that you want, right? So we did some simple algebra, got dy dt all by itself, and we eventually got negative 0.533. Be very careful with your units. These are always important in these problems. Y is measured in feet, time t is measured in seconds, and there are our units. Alright, long video, but hopefully you have a basic understanding of what to expect on Monday and Wednesday when we talk about related rates in class.